shorter and the nights get cold. I like the autumn, but this place is getting old. I pack my belongings and I head for the coast. It might not be a lot, but I feel like I'm making the most. The days get longer and the nights smell green. I guess it's not surprising, but it's spring and I should leave. I like songs about drifters, books about the same. The voice in the main feel a little less insane. Walked on.
Well, it's 5 o'clock. We're live now, and I was announcing this to start at 5 o'clock, so we'll see if anyone shows up. Well, it's 5 o'clock. We're live now, and I was announcing this to start at 5 o'clock, so we'll see if anyone shows up. Well, it's 5 o'clock. We're live now. Whoa. And I was announcing this to start at 5 o'clock, so we'll see if anyone shows up. Let's quit out of that. I should probably mute that video. Well, it's 5 o'clock. Whoa, that's funny. I'll turn that all the way down. Let's quit out of that. I should probably mute that video. Whoa, that's funny. I'll turn that all the way down. Let's quit out of that. Let's see, does that cause all the audio to go away? Good. I should probably mute that video. Wait, we're still getting some of that? I'll turn that all the way down. See, does that cause all the audio to go away? Good. Oh boy. I am not sure why I'm getting all this echo in here. I need to make sure that I'm not pulling in any audio from the system. Let's turn that off. I think that'll be better. See, does that cause all the audio to go away? Good. Oh boy. I'm going to have to edit that out. I'm not sure why I'm getting all this echo in here. I need to make sure that I'm not pulling in any audio from the system. Oh, let's turn that off. I think that'll be better. Then we'll go over here, turn that off, and I think we're set. All right, it says that there are 2 people watching. I think one of the people watching is me. So, who else is watching this? Well, I guess I'll get started. So what I've got on the screen here is the state of the assignment as it stands right now. You'll see there's one new file in there called dump.c. That was the program that I wrote last night in order to debug what was going on. So what I'm going to do is actually reset the project back to the way it was when I first gave it out. That's the bug-ridden version. So I'll do that by looking at the log and seeing that the last version that I had was the buggy version was on Wednesday, and then by Saturday I started fixing the bugs. So what we want is this version right here. So let's copy that version number and we'll say git checkout and paste in that version number. And what that's going to do now is reset the assignment so that the versions have gone back to the way they were. So you see that dump.c file is now gone. So when I gave out the assignment, I had kind of suspected that the Rainbow program that I gave out might have some bugs in it because I didn't honestly fully test it. And so let's go ahead and build this thing. Oops, make Rainbow. And then if we run it, let's see, let's use the rock u100 file. Then we end up with this file. It's not really 600 megabytes. In fact, we go du-h rainbow.bo. You can see it's only using up 400 kilobytes. So it says it's 600 megabytes on disk, but it's really only about 400 kilobytes or so. And so what I want to do was write a program that would go through that file and dump out the content so that I could see whether the file had been built correctly. And so that's where I started, is creating a program that would roll through the file, read in each entry from it, and then display the contents of the entry along with where the location was in the file. So I'm not sure all the includes I'm going to need, but that's a good start there. Here's our standard main. So first thing I need to do is open the file for reading. So let's check to make sure they actually typed in a file name. Argc is less than 2. Then we're going to print out an error message. And exit. Oh, we're using exit, so I know that I'm going to have to include standard lib. Okay, so once we've determined that they've typed in a file name, we can now open it. So let's see, file pointer f equals f open, argv1 for reading, and then if that returned a null, print out an error message and exit. Can't open this file for reading, that's good enough. And exit. Okay, we've got the file open. Now we're going to read it in one entry at a time. And each entry comes from this file here. So let's go ahead and look at that file. There it is. So you can see that an entry consists of a 16-byte hash and a 20-character password. Let's call this dump.c. There we go. So while I know it's going to be fread, but what I don't know at this time is what value does fread return when it reaches the end of the file. So I'll need to go and look at the manual for fread. And it says, okay, on success returns the number of items read. If an error occurs or the end of the file is reached, the return value is a short item count or 0. So that's what we want, is we want to check to see if fread returns a 0. And if it returns a 0, it means we're at the end of the file. So, oops, and I forgot, what was the order of the arguments? Where to put it, how big is that thing, how many elements, and what file are we getting it from? So where to put it, struct entry E. So let's put it in E. One of those things, and we'll get it from F. Okay, so what we're going to do is march through the file from beginning to end, reading in entries, and I only want to display an entry if there's actually an entry there. If I read in an entry and I get all zeros, then I know there's not actually an entry there. So the thing to do is to compare the entry to all zeros. And I think the way I settled on doing this was creating a entry called blank. And then I initialize it to all zeros. Now, if you recall, an entry consists of 16 characters, essentially bytes, plus a 20-character password. And so I could do like this. I could go initialize this thing to 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. 16 of those, and then a blank password. That's a lot of typing. And so I looked up in the guidelines for C99, and first of all, there's two ways to initialize a struct. One is you can list out all the elements like I did there. The other is you can initialize them by their name. So you can say .pass equals, quote, quote, like that. And that initializes the password field to be the empty string. Now, the little side effect is that as soon as you initialize any one field of a struct, the compiler will initialize all the fields. So any one that you didn't list gets initialized to all zeros. So what this has done is it has put in an empty string for the password, and it's put in all zeros for the hash. And so this is kind of a shortcut for listing out all the array elements and the string. So what we're going to do inside the loop here is compare E, our structure we read from the disk, to blank. And if they match, it means that the entry we read in from the disk is all zeros, and we should not display that. So if they don't match, that's when we do want to display something. So let's go. So if mem compare address of E and address of blank and size of struct entry. So, so if that is not equal to 0, that means that the two of them are not the same, and so E actually contains some valid data. So we should print it out then. So I'm going to go printf %x, %s, %s. Kind of want to put a colon there. So this first x here is going to display the location of where we found the entry, so the spot on the disk, basically the array index. And then this is going to display the hash, and this is going to display the corresponding password. I'm going to need a variable for that. So let's put that in there for now. Let's call it index, IDX. And then this will be e.hash and e.pass. So I need this variable. So let's initialize that. And then down here, IDX ++ to make sure we always increment it as we're reading out of the file. And I think that's pretty much it. F close F. I'm just looking at my notes here to make sure that looks okay. Oh, we've got a little problem here, is that the hash is not a string. Remember, it's actually an array of 16 bytes. This password is a string, so it's okay to display it using %s, but the hash can't be displayed with %s. Fortunately, I have a utility function that I wrote called, let's see where it is, down here, digest to hex. You give it the 16-byte array, and it'll return a string to you in all hex. So we're going to make use of that to print out this piece here. So we'll go digest to hex of that thing. There we go. And I think that's more or less it. So let's save that, and we'll compile it. Clang, debugging, dump.c, -o dump, and I know I'm going to have to, oh wait. I'm making use of digest to hex, which is in the md5.c file, so that means I need to compile that in as well, md5.c. I think that's it. Oh, wrong directory. Let's try that again. What happened here? Oh, I need to include md5.h so that it knows about that function. And it says mem compare needs string.h. All right. That's easy to fix. Oh, compiled. All right. I'm going to switch over to the terminal here so that I got more space to see this, and let's run it. Dump rainbow.bow. Well, looks pretty good. Dumped 100 things. Now before I look at the results here, let's see. So word count that, and it says I got 100. So there are 100 hashes in that file, and I got 100 back, so that's good. All right, now let's look at the output. Now something immediately jumped out at me as being suspicious, and that was how the ending sort of looks like the last half of this is wrong. The first half looks like it's part of the hash, but the second half does not. And I think it's actually half, so we can verify that by counting. There's 1 byte, 2, 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7 bytes, 8 bytes. So at 1023 here is where kind of the unique parts of each of these values they look random, which they're supposed to. And it's this A4F066B7 that's the same for every single one of them. So that sort of raised a red flag for me, which is telling me, like, what's going on here? Am I storing the wrong value in the rainbow file, or is my digest to hex not working correctly? Like it's only working for the first 8 bytes? And so I thought back to when I was writing that digest to hex program, and I had written another program that was just simply a test program to make sure that if I pass in a array of 16 bytes, do I get back the correct hex digits? And I verified that, and it worked fine. And I also did the same verification for hex to digest, the one that goes the other direction, and that one worked fine as well. So I was kind of perplexed there as to where the problem was. I'm pretty sure it wasn't with digest to hex, because it seemed to be working okay in my test program. So then I suspected that maybe the problem was with it being stored incorrectly in the rainbow file, which sent me into a panic, because then it realized that none of you would be able to do this assignment correctly because it's all the wrong hashes in there. So I needed to make sure that the values inside the rainbow file were in fact the correct hashes and not these weird ones that end with the same values. So there's another utility called OD. It stands for octal dump, but actually it'll dump out a file in a variety of formats. And if we look at the manual for it, it says here that, if we come down here, -X says that we can dump the contents as hexadecimal 2-byte units. But we don't actually want to do that. We want to dump it out as hexadecimal 1-byte units, because they're just arrays of characters, arrays of bytes. The problem with dumping it out as 2-byte units is that the Intel system is a little endian system, which means the bytes are actually all reversed. And so everything comes out a little bit backwards. So if we go OD-T X1, which says dump them out as hex single hex digits, then we should get the output we're looking for. We'll pipe this into more. All right, so this output here says we start at byte number 0 of the file, and it's all zeros as we expect. And then the star over here means that everything just repeats, all zeros. So it's kind of not interesting output. Here's the first place where we get something that's not all zeros. And there's 008C5926CA. Let's go back and look at the hashes. Let's go here. Here's whatever 008C5926CA, and it ends with 1023 as in the file. And that's the hash for whatever. So 08696CA. Here it is, 1023, and then here's this A4F066. If you recall, that's the last half of the hash in the file that didn't appear to be unique. Let's look at the next one, which starts here. I think it starts here, 0005 F1, and then here again, A4F066P700. So there again is that sort of non-repeating, or excuse me, non-unique repeating value. And then the next one, here it is, A4F066P7. So there it is again. So I can see that every single entry in the file actually has those same 8 bytes in it. So that tells me that there's a bug in my Rainbow program, that it's not putting the correct hashes in there. Somehow it's getting the first 8 bytes are correct, but the last 8 bytes are always coming out the same. And it also tells me that my digest to hex program is working just fine. And it might also be telling me that my dump program is working fine. That's the other thing that concerned me was maybe the dump program's not working correctly, but it does appear to be working because what I see here matches what's in the file. So that means I now need to go to the Rainbow program here and take a look. Why is it doing that? So here's the problem. I'm only copying 8 bytes of the hash into the entry to write to disk. And I don't know what I was thinking when I wrote that, but the actual length of the hash is 16 bytes, not 8. So let's save that. And let's make Rainbow again. Oops, make Rainbow. There we go. And let's try making that file again and then dumping it. And this is what we want to see. Scrolling up, we can see that the whatever password is now correctly, I think it's correct. We should verify that that is in fact the correct hash for whatever. I want to make sure that every byte in here is correct and I'm not missing one. So it ends in 88E2, and the way I'm going to verify that is I'm going to pipe that string into MD5 sum, and we can see that it ends in 88E2 right there. 88E2. Scrolling up. Here, 88E2. Good. So pretty well satisfied that I have fixed that bug. By the way, if you're interested in this command here, this echo is basically like a print command on the shell. You say echo hello, and it just echoes everything back. The -n means that we want to, when we echo this and then pipe it into MD5, we want to eliminate the new line character. So if you say echo -n hello, you get the same thing, the hello, but there's no new line character on the end. You can see that here. But that's in fact what we want to do when we calculate the MD5 sum of a string. We don't want that new line character. So this is the MD5 hash of hello. And you can see if I leave off the -n like that, so the new line character is included, I get a completely different output. So you want to do it with the -n character, or the -n option to echo. All right, so that was the first bug. And then, let's see, what was the second bug? Oh, that's right. Let's go back and look at the output. I had to refresh my memory what the output was, what the bug was. Okay, so as we stated in the assignment, what it does is to calculate the index of where the hash goes in the file, we should be looking at the first 3 bytes of the hash. And like, let's look at Jennifer here. So its location on disk is 1660FD. Remember, that's in hex. And this should match the first 3 bytes of the hash, 1660FE. So it doesn't quite match. It's off by 1. But what I wanted to do first was I wanted to verify, what is that just an anomaly, or does that happen to every single one of them? So let's look at this one here. 1, 2, 3, 4, 5, 6, 7, 8. Its location on disk is 25D559, and the first 3 bytes of the hash are 25D55A. So it's off by 1 also. Now, initially, this didn't really raise any red flags because some of them are supposed to be off by 1. In other words, if I hash the value, stick it in the file, and then notice, and then look in the file and see if there's already an entry there. If there is already an entry there, I should move to the next one and then put it there. So in the case of a collision, I would expect some of these entries to be off by 1. But every single one of them seems to be off by 1. And I'm only putting in 100 entries into this file. I'm not putting in millions of them. And this file should be big enough to hold, I think, on the order of about 24 million hashes, theoretically without a collision. Of course, it's going to collide before that. But at most, we're going to put in 1 to 2 million entries, and there should be 0 or 1 collisions in the whole file. So for all of them to be off by 1, that was kind of weird. So, and especially with only 100 hashes in here, there should be no collision. So none of them should be off by 1. So then I looked back to the Rainbow program. I said, well, why is this thing off by 1? And so I went through the logic of it. So what we do is we hash the string, put it into an entry, extract the first 3 bytes, and I worked through this math again. I was like, maybe the math is wrong. Is this the correct math? And yes, this is the right one. Multiply the first byte by 65536 plus the second byte times 256 plus the third byte. Was I maybe accidentally subtracting 1 somewhere in there? I didn't know. I was kind of perplexed as to what was happening here. Was this looked okay? So the logic here is we're going to move to the location in the file where we're supposed to put the entry. So we seek to that location, and then we read what's there. And we check to see whether that entry that we just read is all zeros. And if it's, if it's not all zeros, then we know that we had already put an entry there, and we need to move to the next one. So that's why I have this loop. This is a do-while loop, so we know we're going to run this at least once. So we come in here and we read the entry that's at the where we had just seeked to. So we read that into a temporary structure, and then we compare that to the blank, kind of like how we did for dump. So we compare that to blank, and here's what one of the bugs is that this is equal to 0, which means that the entry I just read in is blank. So I'm trying to work through in my head again what was happening there. So that means the entry is blank, and if it is blank, it reads the next one. And then if that one's blank, it reads the next one. And so this is actually the wrong thing to do. What we want to do is we want to keep reading entries as long as it's not blank, right? So this comparison was backwards. I should have had this not equal to 0. And so save it. And then run the program. And then try to build the Rainbow file. And then it does this. It just sits there and it hangs. I'm like, well, what's going on there? Why is it hanging? It must be stuck in that loop. Right, that's the only thing I changed was this loop here. So it must be somehow, it reads an entry there, and then it sees that they're different, and so it reads the next one, and then it reads the next one, it reads the next one. I'm going, well, why is this coming out like this? Like, I should be, I mean, well, I guess the first question is, which one is it crashing on? Is it like crashing on the last one? Is it crashing on the first one? So what I wanted to do then was just like print out something. Let's just print out which one we're trying to do. So printf %s. Right, so we're gonna print out the password and the hash, and we'll just make sure those are the right variables. They are, okay. All right, 1, 2, 3, 4, 5, 6. I guess this is okay because remember this comes out to be a 16-byte array, not a string, but it's crashing on the very first one. 1, 2, 3, 4, 5, 6. So that means that, well, I didn't know what was going wrong. I know now what's going wrong, so I'm kind of trying to walk us through what was going wrong. So it must be that it's just reading this thing over and over and over again, and then when it reads that entry off of the file, it is immediately like doesn't match. So I guess the next thing I did was I said, well, what did we actually just read off the disk? Like it should be all zeros, right? This is the very first thing I'm writing to the disk, so the file, so it should be all zeros. So let's just go ahead and print it out. Let's see what I got. %s, %s, I guess. We'll just print out those things. Temp.hash and temp.pass. But remember, this comes out, this is an array, so let's go ahead and call digest to hex. And we'll save that. All right. So this is not what I expected. This is what fread is pulling off the file. It's pulling off this what appears to be complete garbage. This is the hash that it reads, and this thing here is some unprintable character. I mean, it's not even a real string there. So why is fread returning a just as garbage characters? So that's when I said, well, maybe fread isn't doing anything at all, or well, anyway, so I dug into here. So I go man fread, and I go return value. Oh, I should do this. I should go like, what is this thing returning? Maybe it's not returning. Maybe it's returning something other than a success. So I go int, right? So let's print that out. %d. All right, so let's just see what fread is returning. Bunch of zeros. All right. And remember from the manual for fread, it says that this thing returns 0 if at the end of the file is reached or if there's some kind of error. So I know it can't be the end of the file, right? Because it's seeking around. I mean, you can see the file gets really big, right? 600 megabytes. So it can't be that. So it must be that fread is returning an error when it tries to read. And then I thought about it. I said, well, that actually makes sense because when we first create the file has like 0 size. We go and seek to a location. We try to read what's there, and there's nothing there. So fread must actually be returning an error of some sort, saying I couldn't read what's here. And so that's that was the insight into where the next bug was that fread is actually not able to successfully read off the disk, which means that it's not able to do this memory copy. What's happening is the values inside of temp are just garbage values. If you remember up here, where's temp allocated? I forgot there's temp. Oh, here it is. Struct entry temp. So the values inside of temp are just garbage. right? So I'll never be able to, and so fread reads nothing off the disk, so nothing gets written into the entry for temp, and then I try to compare that against all zeros, and of course it comes out to be different. So one of the things to do there was, let's initialize temp. Let's do it the same way we did before, pass equals quote, quote. So now we know that the values inside of this temp entry are all zeroed out. And let's save that. Oops. Oh yeah. Put that back. It actually different this time. So it did continue to print out zeros, but it stopped. So the loop didn't go on forever. So that means that we're on the right track here, that by initializing the temp struct to all zeros, the mem comparer is now able to do its job correctly of comparing that to being zeros. And so if we go back and we dump out the file, we can see that the stuff is in there. But if we look at the hashes, 28F209, 28F20A, they're still off by 1. Look at another one here, 2DCCD0, 2DCCD1. So they're still off by 1, but we're now correctly comparing those entries to blank. So now we got to solve the other problem, which is, why are they off by 1? And I have this line down here which says found a blank spot, need to return to it. So the idea is that if we read in an entry and it was already occupied, we're then going to move to the next entry. And if that one's occupied, we're going to move to the next entry. But at some point, we're going to read in all zeros, and we need to now back up to the to be able to write over that entry we just read in. In other words, we're going to read an entry, read an entry, read an entry. That one's all zeros. Now we need to reverse by 1 entry's worth of file pointer so that we can get back to the spot we were just in. And that's the purpose of this statement here, which is to seek backwards by this backwards right here, the negative, by the size of an entry from our current position, and then we're able to write it to disk. But the problem was in this loop here, fread is returning 0, which means it was never able to successfully read from the file. So the file pointer never got advanced to the next entry. So in that case, if fread returns 0, it means we should not back up one slot. We should stay where we are. We're in the right spot. So in other words, if fread returns 0, it means that there's nothing here. And so this is the correct spot to be writing to. So what we need to do is look at the return value of fread. If it returns a 0, we need to jump out of this loop immediately and write this thing to disk. If it returns a 1, then we do need to back up. And so my solution there, and there's actually probably a better way to do it, but this was my solution late at night, was let's declare this variable outside. And then we'll assign to it in the loop here. And then we'll say if the return value is 0, so if fread returns an error, we're going to break right out of the loop. We're not even going to do this comparison. And then we'll say if the return value was non-zero, meaning fread was able to do its job, then we should back up 1. But if return value was 0, we should not back up. Let me put in here not equal to 0, just to make it clearer. So if the return value is not 0, we'll go ahead and back up. If the return value was 0, we should stay where we are and then write it right to disk. So let's save that. Oops, need to recompile. There we go. Build it and then dump it out. And hopefully we'll see FE75BD, FE75BD. Oh, it looks like that one's in the right spot. FCEA92, FCEA92. So it looks like everything is going into the right slots now. How about this one here, D3FDA? That's got a leading 0 on it. So 0D3FDA. Yep. Looks like everything is going in the right spots. So now that I think I've stomped out that bug, the next thing was to see like, well, I'm only doing 100 hashes here. What happens if I increase the number? So let's open up the makefile and let's go up to the one with 2,000 hashes in it. Oh, I don't need to change it there. Let's just save it. I'll just do it this way. Let's do the one with 1,000 in there. All right, and then we'll dump it. Okay, but I'm interested to see like how many are there. And there's 1,000. That means all 1,000 have been stored in there. And so hopefully if there were any collisions, they went into the next slot. But again, this file should be able to hold about 20, on the order of multiple millions of them without any collisions. And I'm only storing 1,000. So let's go up even higher. Let's do the one with 1 million. Oh, first I need to get that file. So make rainbow 1M. No, it's not called that. Here it comes. Okay. There we go. Now, this is going to take a while. I'm about a quarter of the way done. Well, so while this is working, let me tell you about the next feature I wanted to add to the dump program, and that was what I wanted to know was, were there any entries in that file where the location on the file didn't match the first 3 bytes of the hash, meaning that it didn't get stored in its original location. It got stored in then maybe the next location or location after that. So I want in the dump program to flag those somehow, to put a little marker that says this entry is not being stored in the location where it's supposed to be stored. So if I go back and look at dump, here where I print out the value there, I want to print out like a marker there of some sort. So the thing to do is we need to go and fetch the first 3 bytes out of the digest and then compare that to the location where we are, the value of IDX. And if those are different, we'll put a little marker there. So we'll do something like int I'm not sure what to call this. Let's call it LOC equals, and we're gonna pull out those 3 bytes the same way we did it in the rainbow program. So this is e dot hash 0 times 65536 plus e dot hash 1 times 256 plus e dot hash 2. And then if the location is not equal to the index, I'm basically going to do this. But I'll put some kind of like marker there. Else. So there'll be a star sitting in front of that. And just to make it look nice, I'll indent this as well. Okay. This is done. So let's dump it. And I want to see how many did we get. Oh, all right. There's 90, so there's apparently some collisions. Oh, I didn't compile this. Let's try that again. Nope, that's the wrong one. Huh, that's a very old program there. There we go, it's that one. Okay, 900 of them. Let's actually look at this. Oh, I've done something wrong here. Why is it doing that? Oh, no, that's correct. So I can fix that. If I change this so that it always prints out 6 digits with leading zero. So the zero here means leading zeros, 6 digits in hexadecimal. There we go. Okay, now do any of them have a star? No, not there. I mean, do any of them start with a star? So that's weird. So when we dump it out, we get less than 1 million of them. Let's look at this here. File's the same size. So does this mean there's some repeats in there? Does this mean that the Rainbow program didn't write them to the correct location? Let's go back to the Rainbow program and let's do like else. We're going to print something out. Printf going collision at %d. Oh, let's go %06x. And then we're going to print out, what is it? File location. Is that file location? No, IDX. Okay. There we go. And let's see if this thing ever prints out the word collision. So far, no. So far, no. But we'd kind of expect that if we do get collisions, they might be later in the file because we get fewer collisions at the front, more collisions toward the back. So maybe once we kind of get past the halfway point, we should start to see more collisions. So let's wait it out. Still nothing. Although, now that I'm thinking about it, well, I guess, yeah, I was thinking the real instance of a collision is where, you know, this mem copy comes out to be not equal to 0, not whether fread returns 1 or 0, but let's see what happens. No collisions yet. Maybe there's something wrong with the way I'm dumping this out. If the location doesn't equal the index, print this out, else print it. So this should always print something out. Is that right? No collisions yet. See, I'm actually a little bit perplexed because I wrote basically this program last night, and when I created the rainbow file with 1,000,000 entries there, I actually got no collisions at all. And when I dumped it out, I got all 1,000,000 back, and now I'm getting less than 1,000,000 back. So now I'm wondering what's going on. Huh. 968,958. 968,958. A difference of 31,000. So 31,000 things aren't being printed out. Or 31,000 things aren't being read incorrectly. So how can I count? Oh, what I should do here is when the program is all done, I'm going to print out what the value of IDX is to see if it actually got up to 1,000,000. All right, save that. It's going to print out, yeah, one more because I'm not going to see in the output. So let's just look at the last 10 lines of it. All right. 1677183. Oh, 16 million? Oh, yeah, I guess that's right. Is that right? 16 million. That should be 1 million, wouldn't you think? Because this is basically, yeah, okay, so there's 16 million entries in the file, but I don't know actually how many of them were valid. Oh, so what's happening here is it's reading through the file. There's 16 million slots in there, but only about 1,000,000 of them actually contain real values, but I'm counting all of them regardless. So I need another variable here. Let's call this the count. And then we're only going to increment that in the case of where we print something out here. And then that's what we'll print out at the end, count. All right, let's try that again. Oh, 968,958. All right. So that means, there's only 968,000 entries in that file, not 1,000,000 of them. So is the problem with rainbow or is the problem with dump? Let's see, what could be going on here? So if this is not equal to 0, then we do the fseek and we do a write. If the return value is 0, we're going to break out of the loop. If the return value is not equal to 0, then we're going to do that fseek, but we're always going to write to the disk. Well, now I'm a little perplexed as to what's going on. So when we dump it out, we report there's no collisions. There's no asterisks appearing there. And when we built the table, it didn't say there were any collisions. So I'm not sure what's going on here. This is where I really got to think about this. If return value is 0, we're going to break out of it. Otherwise, we're going to print a collision. As long as this mem compare is not equal to 0, that's correct. If the return value is not equal to 0, meaning fread was able to read something, then we're going to go backwards by one entry, and then we're going to print to it. Let me look at my notes over here. Yeah, the program that I have here pretty much matches what I ended up coming up with last night. That's what I'm comparing it to, is I'm looking at the version that I wrote last night. Yeah, I'm comparing back and forth one. Yeah, looks the same. Looks the same over there. Well, I'm not sure why that doesn't work. Of course, if somebody's watching right now, they could maybe look at the program and go, I see what it is. So maybe the problem was with dump. Maybe that one somehow is not counting them correctly. So if the entry and the blank are different, 65536, 256, 0, increment the count. If the location isn't equal to the index, print it out. It's too bad it'd be really hard to find out which ones are we missing. Like, what are the 31,000 that we're missing? Are they like the first ones, the last ones? Are they scattered around? I'm trying to think about, is there an easy way to calculate that? I mean, we could take the output somehow. It's going to be hard to do. I was thinking if we could take the output of dump, extract out just the passwords, and then somehow compare that with the original file. See which ones are missing. So let's see, Rainbow. We know that Rainbow got all the way up to 1 million, right? Yeah, it did 1 million of them. Let's do this. Let's dump it out, but let's just look at it. So what I'm looking at here is the first 3 bytes. I'm looking for any case where those might be different, indicating there's a collision of some sort. I mean, I'm just visually scanning. Somebody asked the question, mind if I ask what class this is for? This is a C programming course that I teach at Sierra Community College near Sacramento. And we spent most of the semester writing programs to crack passwords by taking a file that contains a bunch of passwords in there, hashing it, and then basically trying to reverse it by brute force, essentially. So this is one of the assignments where we are storing all of the hashed passwords in what you call a rainbow table or a rainbow file, because potentially the rainbow file could be much larger than the amount of memory you have on your computer, so you can't actually read the whole thing into your computer's memory. So you got to leave it on the disk and just use the fact that we can seek to any random portion of the file and pull out the information that's there. I'm not offhand seeing any place where they are different. Of course, I'm going to do this. How many lines do I actually have there? Yeah, 1 million. So there's 1 million in there. So which ones are we missing? And how can we find out? And why are they missing? And why didn't it print out collision? How about if we take out this? Well, no, I was going to say take out the else. Let's just have it print every time. But that's essentially, since we're breaking out the loop, we're already doing that. I don't know, maybe I can do something like here, printf, just something, x. I'm not sure what that's going to do exactly. What I'm hoping to see here is if I ever see an X appear on the screen, then I know that it did this mem compare. Meanwhile, while that's running, let me look at this again. I'm again comparing versions of the programs. Let's see, did this finish? Nope, still working. Do we get any X's? Nope. Oops. Let's see, got anything yet? Nope. How are we doing down here? Almost done, but no X's, meaning we're never getting a collision, which is what I saw last night when I wrote the program. There were no collisions at all, but I'm mystified where my missing 31,000 entries have gone. Okay, how are we doing over here? All million and no X's, so no collisions. I guess I can get rid of that. Well, I'm mystified because the version of the program that I've got here is basically the version that I wrote last night. Variable names are a little bit different, but the structure is the same. And the one I wrote last night correctly comes out with 1,000,000 of them. Well, you know what? Why don't we look at that version and we'll see what happened to it. So, I mean, we basically run it and see if we get the same thing. So I think what I want to do here, if I go git clone, I'm trying to figure out, is there a way that I can just switch to that version and keep the one that I've got? Let's see. Let's copy rainbow.c to rainbow2.c and copy dump.c to dump2.c, and let's go git. This is where I'm not super familiar with git, so git checkout help. No. What I'm trying to do is do a checkout and have it like erase everything that I did. Just check it out. Force. This is used to throw away local changes. Okay, so git log. Oh, no, what I want is the very latest version. How do we get the latest version? Can I say head? Oh, whoops, I was supposed to do a force. Nope. Is this my version or is this the... let me switch over to here. Switch windows. Let's try this. Git checkout C71E388. All right. Okay, so this is the version I wrote last night. And this is the version I wrote last night. So let's take a look. Make rainbow. And let's dump this. So dump rainbow. Count them. Oh, wow. Okay, so the dump version that I wrote last night still dumps 968,000. So that means that something must be different about rainbow. So let's build that one again. Let me not build it. Let's run it again. Now this one doesn't have any kind of diagnostics in there, so it's not going to print out the word collision or any kind of stars or something like that. So I'll show you. Essentially, there's no differences here. So here's that variable that I called ret in the version that I wrote here on the stream, and then I break out of there if that's equal to 0. Here's that mem compare, same thing. Here's that if that return value is not 0, then go ahead and do that negative seek. Otherwise, write to the disk. Looks the same. We're halfway through. Getting there, about 2/3 of the way through. About 3/4 of the way through. Curious to see. As soon as we run this program, I'm going to dump it out and we'll see if we get 1 million back or if we get less than 1 million. If we get less than 1 million, then I'm not sure. All right, here we go. There's 1 million there. Now let's dump it out and count those lines. Oh, 968,000. All right. Well, that's kind of embarrassing because last night, I swear, there was 1 million there. And now I'm missing 31,000 entries. So clearly that's either it's another bug that needs to be stomped out, or I have no idea what's going on. I guess at this point, I've got kind of nothing else to do because you're just going to watch me stare at this thing for a while and try to figure out what's going on. I'd really like to know which ones I'm missing. So I guess maybe that would be something to do, is let's change dump so that, okay, actually, let's see, what should we do? Oh, remember I have dump 2 and I have rainbow. So dump 2 is the one I was working on. Let's open that up. This one here, this is the one I was working on. Let's change this one so that it doesn't print out the location or the hash value. It just prints out the password. So we're just going to go printf %s e.pass. Okay. So now dump. Oh, let's just look at it. Okay, so there it is. It's just the passwords. And if we look in the rocku file, it's just the passwords, but in a different order. So what we want to do is we want to find out which passwords are in the rocku file that aren't in the dump file. So I think, boy, this is going to take a while, is we have to get them so that the files more or less line up. And I really have no idea how long it's going to take, but we basically have to sort them. So we're going to sort, let's dump this into, I don't know, r.out. Okay, and then let's sort it. Sort r.out and put that into r.sort. And boy, this could take a while. Oh, actually didn't take too long at all. And let's sort rocku 1,000,000 into ry.sort. And now let's run a diff on them. And now let's compare them a line at a time and tell us what's missing. Here it comes. Okay, we know held on here. That seems like more than 31,000. Let's count that. What do we got there? 1.9 million. That's not what I wanted. Well, let's look. Head or I'm a goofball here. That's the one we want to do. 62. Oh, I guess that's twice 6. That's okay. That's reasonable. That's twice 31,000. I'm not sure what this is telling us here. Isn't there a program called compare? Oh, that's a byte by byte compare. Compare files line by line. I'm looking to see if there's a way that we can just display the differences. How about a side-by-side? Will that work? What was that again? Dash, no. Output in 2 columns. What does that look like? No, it's not what I want. How about this? Suppress common lines? Well, so the output here is saying that the file on the left, which is the rocku file, contains this word. Round about that line there. Oh, sorry. See, I don't want to see this stuff. I just want to see the words that are different. But anyway, I kind of get an idea now. Skipping ahead. Like this one here. grep 080207 out of the rocku sorted file. It's there. Whoops, sorry, 08. It's there. And out of r.sort, it's not there. So indeed, we're missing some of them. The question is, where did that appear? Is it just like in some random place, or is it all grouped together? So what I want is, I want grep to tell me where those are. Count, no. Zero base, no, I don't want a line number. Here we go, -n. Oh, right, that's not there. Okay, so it's on line 23776, and let's try a different one, like this one here. Two three eight oh nine. We got a question. Does every number have a 0 in front? So the answer is no. Those are just the passwords that people had picked. My guess is that this is something like a date or something like that, like August 2nd, 2007, August 1st, 1991. Maybe it's someone's birth date or something like that. Look at this. August 1st, 1989. August 2nd, 2006. See if we go way down, way down. Here we go. Further, further, further. See, here are ones right there. These are passwords here. All right, so they don't all begin with zeros. Those are just the ones that near the front of the file. So we know for sure there are files in there are lines in the rocku file that aren't in the dumped output. So where did that 31,000 entries go? And they also appear to be in different locations in the file. Oh, I should not do it out of this. I should do it out of this one. Okay, 228248. Yeah, 57036. So they're totally different places in the file. What I was looking for was like, are they all at the end? Are they all at the beginning? But they're all kind of scattered around. So what happened to them? It must be a problem with the, I'm pretty sure it's a problem with the rainbow file, a rainbow program, that it's not somehow storing them in the right place. Well, I guess what we could do, I guess there's a possibility that this fseek is not working. You know, I'm not checking for an error there. I really should be. Fseek back one entry. Oh, where is it? There it is. So what I'm looking for is to see if that ever returns an error. See this one here, I do check for an error there, and none of those ever return an error or print out an error. So those aren't the issue. So this really shouldn't be an issue, I wouldn't think. I know the F write is working. I should check in it for an error there, but I know those are all working because, you know, I get 99% of the entries. How we doing? No errors. Anything? Of course not. So, talking to myself again. We read out of the file. If we're not actually able to read, it means that we're reading from a spot on the disk that, or on the file that doesn't exist yet. Therefore, it's okay to just write to that location. So we can break out of this loop. We're not going to do this. We're not going to seek backwards. And then we're just going to write it. Makes sense to me. Now, what if we did read something? Well, I remember before we'd put in there a print so that if it did read something, if fread actually returned a 1, then we should have printed out something, but we never get that either. And we tried to print out something right before the mem compare happens, and we never get that. So we get no collisions at all, which kind of makes sense. I mean, we're putting 1 million entries into a file that can hold about 24 million. So, I mean, you'd think that there's like a 1 in 24 chance or something. I don't know. I don't know what the chances are, but, well, maybe it is. 1 in 24 chance that there will be a collision, but nope, none. Are we somehow not able to write to the disk? Let's check that. If not. How do we do? Yep, no errors there. Well, you know, this is the kind of bug that keeps programmers up at night. It works for the 1,000 entry, it works for the 2,000 entry program. It doesn't work for the 1,000,000 one. It's missing some of them. Just a few of them. You know, 31,000 out of 1,000,000. It's not missing too many, but it is definitely missing some. And where are they? And which ones are they? We've put in all sorts of print statements to try to figure out where it could be missing some. Nothing. No output here saying it's can't write, can't fseek. We put in ones here to check to see if we couldn't read. Those all worked. How we doing? No error messages. You know what I'm going to do next? We know what some of these entries are that don't work, right? You know, like this one. Oh. So I'm going to scroll every time I output something. Now what I was thinking about doing was, I know one of these entries doesn't work, so maybe in the program, I can do a string compare. And if we ever come up with that particular string, that particular password, then we are going to print some more stuff out. See, no messages saying that it couldn't write to the file. All right, I want to, just out of curiosity. Dump. Count them. There they are. They're missing. Okay, so what was one of the ones that we were missing? Let's just pick one. Pick one that's interesting. Here. 2233 red. So here we go. If string compare 2233 red, comma, password. What should I print out? Red. Okay, so that tells me that we are looking at that one. Okay. And then, oh, let's set a variable here. Red equals 1. And red equals 0. Okay, so if this is 1, then we can go like if red printf %d x. I don't know. Don't know if I should print that out. Actually, let's print it out in hex. 06x. If red printf seeking to %d if red printf red f read equals %d. Sorry, the reason why this is a different variable than we had before is because now I'm using the version that I wrote last night. So I apologize. All the variable names have switched on you. All right, let's see. Let's see what that does. Make rainbow. Ah. What happened? Oh, missing the parentheses. There we go. Ah, whoops, stop. Else red equals 0. So I didn't reset that variable back to 0 after we've already done the red one. I only want to print out the result. I want to print out this stuff for just one of the entries. Oops, I forgot to compile again. Stop. There we go. Hey, okay, why is it doing that now? Of course, way off the top. Oops. Silly me. There. Probably would have been better to find out one that appears toward the beginning. So what should we see? What we should see is for this particular entry, it's going to tell us what the location on disk is, and it's going to tell us whether or not there was something there already. Ah, okay. Oh, stop it. Okay. So the index is 40. Oh, let's do this. Echo -n 2233 red. So 40. So that's the correct 4005E3. So that's the correct index. And then this value here is basically this number times the size of an entry. So we seek to that location. If we return 0, meaning there wasn't something there, okay, so that returns 0. So that means we should break right out of the loop. And it's not going to do this, so we should just write it. And yet, if we dump it, wait a minute. Why is that there? Oh. So you can hear in the background it's pouring outside. And I've got the door open so my cat can get in and out. So that's why you can hear the rain. Okay, so the reason why it appeared there was, I remember I boarded this early. So 2233 red must have gotten written to the file. And then later on, it gets overwritten. So there is some kind of collision. So back over here, let's go int red IDX. Okay, so if red IDX equals IDX. So I'm gonna remember that one. Okay, so I'm gonna remember that one, and then if I ever come up with that one again, I want to print out what the password is. That's what we'll do. Okay, so if not red and red IDX equals IDX. Printf %s. Let's go not red. %s. Password. Okay, so I want to know what password had the same index as that red one did. Okay. Now we get to wait because we know that this one appears at 540,000, and so the next one is going to appear sometime after that. So I guess what this is telling me is that maybe approximately 31,000 entries do actually collide. But something in the logic of my program is throwing them away. Okay, there's the red. Now, I'm going to watch for another one that pops up. There it is. So glad that that wasn't some naughty word. All right. So this password overwrites the other one. Let's see if another one comes up. Almost there. All right, I didn't think another one was going to come up. So let's do this. Echo. Spell that correctly. Okay, and then echo -n. What was it? 2233 red. Huh. All right. So this is weird. So the calculated index of. Okay, did I get that right? Oh, there's only one L. All right. Okay. So the calculated index of these two passwords are the same. So that's a collision right there. So my collision detection is not working right. So why don't we just restructure this? Let's not do the mem compare at all. Let's just say if I do an F read and that comes out to be a positive hit, so I'm able to do the F read, it means that something is already there. And then I need to scan forward to the next one. All right, so I want to preserve this. So basically, while fread result It's not equal to 0. Well, actually, I can just do, well, 1. So we'll just do this for forever. But as soon as fread all right, so let me think about this. So we're going to read if that is positive, meaning we were successfully read, we're going to skip out, just break out of this thing. If we're not able to read, yeah, this is kind of weird. Let's just remove that. So if while fread result. So while that is a 1, keep reading. And then if we did get a 1, seek back 1 position and then write it to disk. However, if we got a 0 back, don't seek back a position. All right, well, let's give it a try. That's a warning, so that's okay. Here we go. Gotta wait. I was really only expecting I'd be here about an hour. Now we're going on an hour and 45 minutes. So, but we're tracking down this bug, and hopefully, if we get this bug tracked down, then we'll have solved this for good. Okay, in less than a minute, we should see that first one come up, that 2233, and then about a minute later, we should see the next one come up. So there'll be no difference in the output, but hopefully, we won't overwrite the entry that's already there. Okay, there's that one. There's that one. You know, there really isn't a way, given the way this program is written, to make it go any faster, because we're just writing to disk constantly. There are, of course, better ways to do this, but I wanted to keep it simple. All right, almost done. All right, now let's see. This better say 1 million. This doesn't. Still says 968,000. And then if we go grep 2233 red, it's not there. And that one is there. Well, so that didn't make a difference. Oh, So maybe we don't need to do this fseek anymore at all. So as soon as fread result returns a 0, no, as soon as fread, yeah, as soon as fread result returns a 0, boom, we're just going to write it there. We don't have to back up one at all. All right. Now the waiting game again. We got a comment. It says, you're at the end of the file. That's a good thought. But that's what the fseek is supposed to be doing, was we're basically making what's called a sparse file. So we're allowed to seek beyond the end of the file. And then as soon as we write there, then the operating system will allocate that block on disk. So and the reason why I think that's what's happening is because when we first start out, the file is of 0 size. So the first seek that we do is immediately beyond the end of the file. And then we're allowed to do the write there. So I think that should be working correctly. Unless you mean we're at the end of the rocku file. But that's something we haven't really considered yet, although I think it's working right. Anyway, we're going to find out here in a moment. I'm really hoping this is it, that commenting out this seek to go backwards is going to fix the problem. All right. Oh, about the fseek I removed, the one I commented out there. And you mean like I'm at the back end of the file, or I'm at the front end of the file? Like I'm seeking into like negative territory. Anyway, let's dump this and count the lines. Ah, what? How can that be? Okay, that one's there. That one's not there. Ah. I did like recompile the program, didn't I? Like I'm not running the old version, am I? Yeah, I did recompile it. Okay. So I, going over the logic here again, I attempt to read from the file. If that returned a 0, I should be breaking out a loop immediately, and then I immediately write it to disk. If that returned a 1, then I'm going to go back and read the next entry out of the file. And that one should hopefully return a 0. And I should immediately break out of here and write it to disk. So I'm once again, I'm flabbergasted here as to why this is not working. So attempt to do a read. Read fails because the block hasn't been allocated yet. Loop back, do another read. Oh, excuse me, the read fails. So I'm going to break out of the loop, write it to disk. Read succeeded, which should happen in the case of the other one. Oh, let's do this. Let's go like if read result. Oh, sorry, f read result. If f read result. So if that returned a 1, so what I'm trying to do is investigating. Does it actually return a 1? If read equals 1 %s. I'm going to print out the password. And I think we discovered this thing like never prints out anything. So the fseek I removed is at the end of the file. Is that the problem? You mean like maybe the entry I'm putting in is the very last one in the file? I'm going over in my head how that would not work. All right, there's that one. There's that one. Now see, that should have printed out something else. That should have printed out this message. Oh, sorry, this message. But it didn't. So when there's a collision, fread apparently still returns a 0. I mean, could it be something like the file's not flushed out, and therefore when we read from it, we don't get anything? I mean, I imagine this is going to like really slow things down. Well, let's try that. Let's put in a flush. I hate doing that. Is it going slower? Actually, it doesn't seem to be going that much slower. All right, there's that one. Now notice at this point, we still haven't seen any messages saying that fread returned a 1. Now, when this other one comes up, now see, we don't see that message. That's somehow telling us that even when there is a collision, we don't detect it. I'm looking at this here. Nothing. Nothing at all. So apparently fread always returns 0. On success, fread returns a number of items read or written. So it should return a 1, or it should return something other than 0. This number equals the number of bytes transferred only when the size is 1. Okay. fread does not distinguish between end of file and error, and colors must be and error determine which occurred. That doesn't matter. I don't think that matters. See, if we get a collision, then when we do an fread again at that same spot, it should return and say, there was something here. But it's not. It's returning 0, saying there's nothing here. I guess I can take that out. Didn't make any difference at all. So why is this returning? Why is fread returning 0 when there's data there? I've used the word mystified, flabbergasted, and perplexed, and I'm all three of them, and I don't understand why fread returns 0 even though there's something there. I mean, I do the seek right here. Seek to that spot. Read it. fread is always returning 0. I'm going to Google here for fread sparse file. I don't see anything there. fread returns 0. Why does fread always return 0? I'm checking that. Right in binary. I'm sitting here on Stack Overflow, of course. And there is a question that says, why does fread always return 0? But this is a person who are you sure your file has a size greater than 50,000? Yeah. That didn't really tell me anything. Well, look at another one. none of these really are answering the question. Because, see, the thing is that, fread is supposed to return 0 most of the time. The problem is that it's not. It is still returning 0 when it's not supposed to return 0. And so all the questions I'm looking up say, like, why does it always return 0? Well, it always returns 0 because, like, you're in the file, or you're not reading in enough bytes or something like that. But this is a case where 99% of the time it's supposed to return 0. It's that 1% of the time when it's not supposed to return 0, when in fact it is returning 0. And so that's what I'm confused about. And I'm doing a flush at the end to make sure it's written to disk. Well, I am going to give up for now. I'm gonna probably think about this, debug it some more. You can stare at me for a while. I'm not going to get anywhere because I think this ought to work. So I'm going to, this has been going for over 2 hours now. I'm going to call it and then probably work on it some more. And then hopefully maybe in the comments to this video, I'll describe what I found. All right, so I'm kind of like no further along now than I was over an hour ago. I still don't know why this is losing 31,000 entries. Well, actually, we know why it's losing 31,000 entries. It's because that's where collisions are occurring. That's where hash collisions are occurring. But why doesn't it detect that error? That I don't know. And this is the only way I know of to detect that problem, or detect when that happens, is to do a read from the file. And if that read successfully returns something, we know something got written there, and so we should skip to the next entry. But for some reason, fread is returning 0, saying that nothing is there all the time. And that's when I don't know what's going on. Well, thank you. Yeah, pretty late where you are. It's very late where you are. Yeah. This video will get posted on YouTube, and so check sometime, and I'll probably describe what I found, and hopefully we'll all learn something. All right, so that's it for now. I'll see you next time.